In the fourth and final part of this lecture, we will discuss nonlinear regression. Sometimes linear models cannot capture the patterns in the data correctly, and we will show that using an example of prediction of age from 6 brain tissues. First, we will look at the first feature, cortical volume, which is plotted here. And if we fit a linear model to this data set, we see that it fits quite well, and we have a cross-validated R2 score of 0.88, which is quite good. But still, let's have a closer look at this plot. Which type of error we have? Bias, variance, or noise? Think about that for a minute. So this time we do have bias error. If you look at the youngest babies, the predicted ages seem higher than what we would expect when looking at the plot. So we have positive bias. Now, the variance error is unlikely there because we have a model of low complexity, but we do have noise, but there is not much we can do about that. Because we have the bias error, we can try to change a model to see whether we can improve the predictions. So we can try to reduce the bias error by fitting a nonlinear model, and we see that that worked. So the bias doesn't appear there anymore. And this is also confirmed by quantitatively. When we calculate cross-validated R2 score, it will raise to 0.9. So how we can formulate a nonlinear regression model? Nonlinear regression can be viewed as nonlinear feature transformation followed by linear regression. Nonlinear transformation will be denoted by phi, and our prediction model will then become phi x, which is our transform feature vector, transposed times w, which is our parameter vector. Let's look at the example of polynomial regression of second degree. So we already know what feature transformation looks like for a one-dimensional feature vector x. So transform vector phi x will be a vector 1, x, and x squared. And then we can calculate the prediction model, which is phi x transpose times w. And we see that we arrive at the equation of the polynomial model of second degree. In 2 dimensions, when we have 2 features, x1 and x2, we will end up with 6 features after feature transformation that are various combinations of the original 2 features. And then the prediction model will be linear with 6 parameters, 1 per feature. So remember that feature transformation usually increases the dimension of a feature vector. And we have already seen that in case of a univariate polynomial regression when one-dimensional feature vector x was transformed to m plus 1 dimensional feature vector, where m is the polynomial degree. So what will the loss function look like? So we can again use sum of square errors between expected target values and predicted target values, but this time we will use the modified prediction model. And it is also useful to add a reach penalty to the loss function, because as we said, feature transformation often increases the number of features, so overfitting can easily become a problem. Here in this example, we can see how reach penalty can be useful for polynomial regression. This is again the data set of cortical volumes. And we see that if we fit the polynomial of 10th degree, it fits quite well, but there seems to be a little bit of overfitting. We have cross-validated R2 score of 0.88, which we now know can improve. So if we include reach penalty with lambda equals 0.25, we see that overfitting has been reduced and cross-validated R2 score has raised to 0.9. So we have a better model. It is useful to express nonlinear regression in matrix formulation. Our original theta vectors in the training set are xi, and then the transform features will be denoted as phi xi. And now we can form the transform feature matrix. It will consist of row vectors f phi xi, so we will put our transform feature vectors in the rows of this matrix. Okay, so we can now write a nonlinear ridge regression loss. It will be exactly the same as the linear ridge regression loss, except that we replace the original feature matrix X with the transform feature matrix phi. Now we will solve this nonlinear regression problem by minimizing the loss. And there is analytical solution that is the same as for a linear problem, again with original feature matrix replaced by transform feature matrix. Polynomial ridge regression can be implemented in scikit-learn as a pipeline of 3 objects. The first object will be polynomial features, so polynomial feature transformation, and this time will not include the intercept. We can do it by setting parameter include bias to false. Bias is just another name for intercept and shouldn't be confused with bias error. Then next object will be standard scalar to normalize the features after transformation, followed by ridge regression. And we will keep the intercept in ridge regression because it is not penalized, and that way we will obtain better solution. We have 2 hyperparameters to tune, polynomial degree and alpha, which is the strength of ridge penalty. And we can use grid search CV to find the optimal parameters as usual. So let's now see how polynomial ridge regression performs for our 3 dataset. And we can see that for a single feature and 86 features, the performance of the models didn't improve much when we changed from linear to nonlinear. Actually, for 86 features, grid search CV selected polynomial of the first degree, so the linear ridge model that we had previously. However, for 6 features, the performance improved significantly. We now have 0.83 weeks root mean square error after cross-validation. And this is a significant improvement to original 1.17, the best performance, or 1.27 that we had for 6 features. So it appears that in this data set, there must have been some nonlinear patterns. Kernel trick helps us to design more versatile nonlinear regression models. And to be able to use kernel trick, we will define the dual representation A of our model parameter vector W. This means that our model will be parameterized by vector A rather than vector W. Important thing to note is that the original parameter vector W has D elements, 1 per each feature, while the dual parameter vector A has N elements, 1 per each sample. Then we will introduce this dual representation into the prediction model, which is phi transposed X, the transform feature vector, times W, the parameter vector. And if we do that, we will be able to define the kernel, which appears here. And this kernel represents a similarity between 2 feature vectors. So in this case, is the new sample with feature vector X and the training sample with feature vector Xi. So the most common kernel is a Gaussian kernel, and you're very familiar with that. And when the feature vectors are multivariate, we calculate Euclidean distance between them and input that into the kernel. So let's have a closer look at our dual prediction model. Here you can see that there are similarities, these kernels, between the new sample and the training samples. And we can see these kernels here placed around the feature vectors of the training samples. And then we multiply them by elements of the dual representation and sum them up, and that will give us a curve. And in this case, the kernel is too small, so the prediction curve is not very good. But if we enlarge them a bit, we have a nice curve going through these three samples. And if we enlarge them further, then we'll get a smoother model. So how do we find this dual representation? So to do that, we will introduce it into the nonlinear rich regression loss, and that will give us this type of formulation of the loss. What appeared here is a matrix K, which is called the Gram matrix. You see that it's related to nonlinear, nonlinearly transformed feature matrix. And this matrix K is a matrix of all the similarities between pairs of training feature vectors. So it will have size n times n. And if we minimize this loss, we will obtain analytical solution for the dual representation, which is written here, and you see that is a very simple formula again. So we will also write a matrix formulation of the prediction model, which will be vector k x transpose times the dual parametrization A. And this vector kx will be vector of similarities between the new feature vector x and the training samples x1 to xn. And the full prediction model is then written like this analytically in a simple equation. So to evaluate this model equation, we need to calculate similarities of the new sample with all the training sample. So the good thing about that it's non-parametric, therefore very flexible and can adapt to the data. But the disadvantage is that if a number of samples is large, so for example, much larger than number of features, the model is much slower to evaluate than the traditional model parameterized by W. So let's look at an example. So we have 3 training samples. Their feature vectors are -1, 0, and 1. So we have a single feature and the target values are 2, 3, 2. We use Gaussian kernel and we have 2 hyperparameters, sigma, which is standard deviation of the Gaussian kernel, and lambda, which is strength of the rich penalty. And if we keep lambda fixed and keep increasing sigma, we see what happens to the curve. So for a small sigma, so small kernel, some predictions tend to 0, which is not a very good fit. And if sigma is large, then we are underfitting the model. Now we fix the parameter sigma and increase lambda. And we can see that for a larger lambda prediction 10 to 0, this is because unfortunately kernel rich penalizes the intercept. So solution to that could be to zero center the target values. Now let's have a look at some other kernels. So in some cases we can calculate them, like for example, linear kernel. It is because we know linear feature transformation. It is given by a vector 1x, so it is for single feature x. And we can then directly calculate the kernel. So if we have a feature x and a second feature x prime, then we calculate it as phi transposed x, phi x prime, and it will give us 1 plus x, x prime. And if we use this kernel in kernel rich regression, we get linear rich regression. We can do the same for a polynomial kernel. So we know polynomial feature transformation, and I use here an example of second degree. So we have transform feature vector 1x x squared. And again, we calculate the kernel as phi transposed x 5 x prime, and we get 1 plus x x prime plus x x prime squared. And with this kernel, we get polynomial ridge regression. So you see that we fitted a parabola to these three samples because we have second degree. Kernel ridge regression is implemented in scikit-learn through object kernel ridge. And the parameter kernel defines the type of the kernel. And if we set it to RBF, which means radial basis function, that will give us Gaussian kernel. We have two hyperparameter gamma, and this sets the inverse width of the kernel. So it's 1/2 sigma. So large gamma means small kernel and the other way around. And alpha is the strength of ridge penalty as usual. And we need to find these two hyperparameters using grid search CV. Let's now revisit the example of the prediction of age from volumes of 6 brain tissues. So unfortunately, we cannot plot the fitted models because we have 6-dimensional feature space. But what we can do instead, we can plot expected target values versus predicted target values. And obviously, for an optimal model, this would be equal. So they would lie on this red line that shows target values equals to predicted target values. And we can see for case of linear ridge that for the higher ages, the points are actually quite close to the line, but not for the younger babies, they deviate. So we have a bias error here. And if we, there we go, and if we apply a linear model, instead this bias is removed and root mean square error with cross-validation is improved. And the best performance is for kernel ridge. We have a cross-validated root mean square error of 0.77 weeks, which is by far the best we obtained. So all the examples that we've seen in the lecture are available in the tutorial. The mandatory tutorial contains 3 notebooks: multivariate linear regression, penalized regression, and nonlinear regression. There are exercises 1 to 4, and the solutions are available as videos on Kids. There is one optional notebook with exercise 5, and here you will implement your own kernel ridge regression. This exercise is highly recommended because it will improve your understanding, hopefully. And solution to this exercise is available as Jupyter Notebook. So one last thing that I will ask you to do during this lecture is an exercise, and this is a written exercise. It's very important. It's preparation for the exam. So we have our 3 training samples that we already seen. So the training feature vectors are just single features, -1, 0, and 1, and with associated target vector 2, 3, 2. And now you are given Gaussian kernel and hyperparameters sigma equals 1 and lambda equals 0, and you are asked to predict the target value for the feature -0.5. So this one using the kernel ridge regression. So what you want is this value here, this data point here. So the way you do that, you will first calculate the gram matrix K, then the dual representation using this equation, then you calculate the vector Kx for x equals minus 0.5, and finally you evaluate the prediction. So you are expected to write this on the paper, calculate it by hand. The most complicated calculation is inversion of this matrix, which is 3 times 3, so you should be able to do that. But if you have problem with that, you can use computer for that. The solution of this exercise is available on Kiza's PDF. And this is the end of the lecture. Thank you for listening.